Welcome to our next segment, questions 8 through 13. Question 8, I don't even know if it's on the bottom of this or not. Yes. We're going to match scientists, but you'll notice on your worksheet I forgot to list the scientists. So let's go back in time and do a little history lesson. Democritus, not a scientist, but Democritus was a Greek philosopher who came up with the idea of something that cannot be broken, indivisible. He called that the atom. All right, fast forward 2,000 years later, John Dalton did a whole lot of experiments, a lot of gases, came up with the current accepted way we describe elements and compounds. His atomic model said that it was a solid sphere. Fast forward 150 years, we come to Thomson. Thomson did the cathode ray tube experiment, and he discovered that there were little negative particles, even though overall the atom was neutral. So he described this like a plum pudding, or what you and I would think of as a chocolate chip cookie, and that the plums, okay, if I can spell pudding, the plums were the negative particles, and then the rest of the pudding was the positive matrix. Shortly after that, Rutherford conducted his famous gold foil experiment, in which he shot alpha particles, which were radioactive particles, at a piece of gold, and had film on the other side to record where the alpha particles hit. He expected them all to go through, and most of them did, but he discovered that some bounced back. So there had to be some small, solid piece in the center, and this was the nucleus. Okay, so he came up with the idea of the nucleus and that it was positively charged. Our last scientist that talks about molecular structure, and there's more than this, but the last one we're going to talk about, in the early 1900s, Bohr came up with the planetary model that the electrons circled the nucleus in definite paths. Quantum physics figured out, no, it's not definite paths, it's based on how much energy they have, blah, blah, blah. We're not going to worry about that, for now at least. All right. What is an isotope? An isotope is basically any kind of element that has atoms with different masses. Why do they have different masses? Because they have different numbers of neutrons. Carbon-12 has, oh, I lied. Carbon-12 has a mass of 12, it has 6 protons. Carbon-14 has a mass of 14 and has 8 neutrons. Okay, so your mass number is equal to the mass, is equal to the neutrons plus protons. And the protons, mass number minus protons gives us neutrons. All right, so true or false? Protons and neutrons are equal for atoms that are ions. False. Ions simply mean they have a charge, but protons and neutrons do not have to be equal. They are, in a lot of cases, early on in the periodic table, but as soon as you get past element 20, they're almost never equal. Isotopes are elements with the same mass, but different atomic numbers. Again, false. If it's the same element, it's going to have the same atomic numbers, and it would be an isotope. So that one is also false. To make it true, you would say isotopes are elements with the same atomic numbers. Third one, the mass number is the sum of protons and neutrons. Ding, ding, ding. That is true. The atomic number is equal to the atomic number of electrons. That is true sometimes. If we are talking about ions, it is not true. But if you're talking about neutral atoms, it is true. Finally, all atoms of the same element have mass number, which doesn't even make sense, have the same mass number. That is false, 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 because that's what the definition of isotope is. Nuclide symbol is what I drew up here for my carbons. So we wanted to have a nuclide symbol of an element with 18 protons. That means it has an 18 on the bottom. The top number represents mass number. Mass is protons plus neutrons. So that would be 34 total. The element that has 18 protons is the element argon. Next question. On the periodic table, why do we have elements with fractions? Why is boron 10.8? Carbon 12.00011? Well, it's not because you have parts of neutrons. It is because we average. We have to average all the isotopes. The way to calculate that, you take the percent abundance times the mass for each isotope. So if you have 3 different isotopes, you would do... Here's a quick example from our notes. Here are 100 neon atoms. We have neon 22, and we have one, let me get a highlighter, 1, 2, 3, 4, 5, 6, 7, 8, 9. So neon 22 has 9 atoms out of 100, or 9%. Neon 20 has 10 neutrons. I'm not going to count those. I'm going to go on and do neon 21. Neon 21 has just 1 atom. So that's 1 out of 100, or 1%. If that adds up to 10%, that must mean we have 90% neon 20. So these are our percent abundances. We're going to multiply them by the mass. If neon 22 has 12 neutrons and 10 protons, it would have a mass of 22. So we'll take 99 times 22. We'll take 90% times 20. And we'll take 1% times 21. $1,800 and $198. Add those up. 20.09 AMUs, atomic mass units. Okay, 20.09 is the total average. Some people want to look at this and add these all up and divide by 3. Well, that would be okay if they were equal, but you can't do that. You have to do percent abundance times the mass. All right. Last question, 13. Which has the greatest number of electrons? All right. Aluminum with a +3. Aluminum's atomic number happens to be 13. 13. The charge is equal to protons minus electrons. So if our answer is +3 and we have 13 protons, we just simply solve for x. How many electrons would that be? 10 electrons in an aluminum plus 3. Aluminum itself, if it has 0 charge, protons and electrons are equal. So this guy, I'm going to move that over here, this guy has 13 electrons. All right. The next guy, phosphorus with a -3 charge. Phosphorus has 15 electrons. So 15 is, oh, I'm sorry, -3 is equal to 15 minus E. Well, if we solve for that, we would get 18. So phosphorus with a -3 has 18 electrons. Magnesium with a 2+, there are 12 protons in magnesium. So 2+ equals 12 minus E. You're going to have 10 electrons. Thank you very much for this segment of Learn Your Chemistry.